will be,
ARM Flexible Access for Research opens up a world of new opportunities for academic researchers by providing free access to a wide range of cutting-edge ARM technology. Whether your research focus is security, machine learning, or analog and mixed signal designs, you will benefit from real-world, commercially proven processor IP for microcontrollers, application processors, graphics and systems IP, and resources to drive your research forward. ARM Flexible Access for Research empowers academic research teams to experiment and innovate with quicker, simpler access to complete RTL subsystems and tools, enabling academic researchers to open up new opportunities and possibilities for high-impact research projects. We've made it faster and simpler for the academic research community to start using ARM IP. It's never been a more exciting time to drive your research forward with ARM. Learn more at arm.com/flexible access for research.
Okay, so we can we start, John? Are you ready?
I am, yeah, sure.
Okay, so while I introduce you, maybe you can bring your presentation on the screen, and then we go ahead. So it's a great pleasure to introduce Professor John Rogers. He is Louis Simpson Kimberly Query Professor of Material Science and Engineering, Biomedical Engineering and Neurological Surgery in Northwestern University. He is one of the pioneers in the field of flexible electronics, one of the early researchers who started this field. He obtained a BA and BS degree in chemistry and physics from University of Texas, Austin in 1989. From MIT, he received SM degrees in physics and chemistry in 92 and PhD degree in physical chemistry in 1995. From 95 to 7, Rogers was a junior fellow in Howard University Society of Fellows. He then joined Bell Lab as member of technical staff in 1997 and served as the director of this Department of Condensed Matter Physics Research from end of 2000 till end of 2002. From 2003 to 2016, he was on the faculty at University of Illinois, Urbana-Champaign, and where he held a Swanlund Chair, which is one of the highest chaired position in the university, with a primary appointment in Department of Material Science and Engineering, and joint appointments in the Department of Chemistry, Bioengineering, Mechanical Science and Engineering. From there, he moved to Northwestern University, and in terms of research, he has lots and lots of papers. I can see from CV, I'm sure that number must have increased by now. So I can see more than 550 papers and over 100 patents and patent applications. More than 70 of these applications are licensed or in active use by large companies and startups that he has co-founded. So his research has been recognized by many awards, including Smithsonian Award for American Ingenuity in Physical Sciences, Lemelson MIT Prize, MacArthur Fellowship, and he is member of National Academy of Engineering, National Academy of Sciences, and American Academy of Arts and Sciences. John, over to you.
All right. Hey, thank you very much, Ravinder, for that kind introduction and for the invitation to share with the group some of the things that we've been doing in my research group here at Northwestern University. I'll focus on advanced wearable devices, that is sort of skin-coupled electronic and microfluidic systems that have the capacity to provide ICU-grade monitoring of physiological status, but outside of a laboratory or clinical setting. So that's kind of the vision, is to move ICU grade technology into the real world for continuous monitoring to allow for improvement in the way that we deliver healthcare ultimately from a cost and an efficacy standpoint. So I have about 45 minutes worth of content in this slide deck. I'll start with a background, a motivation, and a summary, just a quick overview of some technical approaches that have worked well for us in this space. But the bulk of the content of the talk will really focus on system level implementations of those technical approaches. So I'll try to give you an idea of what the state of the art looks like, or what the capacity for these technologies actually is in the context of clinical needs. I'll focus on two platforms. One is an electronic set of systems that are skin-like in their construction that embed wireless biosensors for use on really a wide range of types of patients and various types of conditions. I'll give you a sense of the extent of deployment of those devices and maybe some future opportunities for continued research in this space. And then kind of conclude with what represents a little bit newer effort for us, where we're thinking about not only electronic capabilities in these platforms, but also kind of lab on a chip, microfluidic type technologies for capturing and storing and performing biomarker analysis on biofluids in general, but sweat in particular. So as was mentioned in the introduction, I'm here at Northwestern University. My core expertise in my home department is material science and engineering and biomedical engineering, but we run a fairly interdisciplinary group that cuts across almost every traditional area of engineering study, but also couples very strongly into the medical space in medical technology. And so I have an appointment in our medical school, and we have very deep engagements across many departments associated with our medical school. And I'll try to highlight a few of those as I move through the content of the talk. And then finally, of note, we have an institute for really sort of enabling research at this interface between engineering and medicine, which I think is a very fruitful area of research. It's an institute for bioelectronics, and it's a newly endowed organization for which I serve as the director. So the overall thrust here is to think about reformulation of microsystems technologies, microelectromechanical systems, microfluidic structures, photonic systems, optoelectronic technologies, electronic integrated circuits, into forms that really will allow for chronic integration with soft curvilinear textures of the human body ultimately, but living systems more generally. And you can think about the opportunities maybe in the context of the brain, which is biology's most sophisticated form of electronics. There might be a lot of utility in creating classes of man-made systems, man-made electronics that could interface with the brain as research tools for investigating the underlying operating principles of the brain, but also maybe engineering platforms for treating disorders of the brain by electrical stimulation or targeted pharmacological delivery and so on. And so that might be the first place to start, just to kind of orient you toward the goals of our programs. But if you could generate an integrated circuit technology, for instance, that could laminate in a soft capacity on the textured surface of the brain, then you probably wouldn't stop with the brain. You'd think about other vital organs of the body where integration of that kind of technology might have utility. And so we've done a lot of work thinking about integration with the heart. The cardiac system being an electromechanical system, what could you do with electronics in terms of sensing of electrophysiological behaviors associated with cardiac cycles, or maybe very advanced forms of stimulation to eliminate arrhythmias, for example. Same types of technologies developed for the brain could have utility in that context. So other or internal organ systems as well, such as the peripheral nervous system, the spinal cord, the kidney, the bladder, the lungs, other places where we have active programs. But I'll really focus today on integration with the largest organ of the body, the skin, because of its capacity for non-invasive device integration, and therefore more rapid deployment and transition out of a laboratory and animal model setting into a human patient population. But the same core ideas would have applicability there, where you're thinking about a wearable device, but not anything like a Fitbit or an Apple Watch, something that would look more like a kid's temporary tattoo or a Band-Aid, to allow integration, not only at the wrist or the hand or the finger, but really any location across the body matched to measurement need, really choosing the anatomy not based on convenience of coupling of the device to the body, but places where you can capture signals relevant to the clinical requirements associated with a particular condition that you're interested in. So those are the ideas. And if you think about integration with biology, it might be useful to at least contemplate some of the underlying design principles, the engineering strategies that are kind of present in biology, and not necessarily with a goal toward mimicking and reproducing exactly those engineering features, but just thinking of abstractions of those kinds of concepts that could be embodied in the near term in man-made systems to facilitate that integration. And if you think about the engineering kinds of designs that are present in biology, it's really mind-boggling, the level of complexity. It's cutting across length scales all the way from the single molecular scale to macro scale, meter scale dimensions. It's hard materials integrated with soft materials. It's really functional 3D assemblies of different kinds of materials and structures and tubes and electrical communication networks, fluid transport systems. It's responsive, reconfigurable, and so on. And so reproducing those features is not likely, within the realm of possibility, at least say in my lifetime, but you might be able to pick out certain features and begin to embody those in man-made engineering systems to facilitate integration, as I mentioned before. And so in that broader context, in my group, we kind of have three thrust areas with an eye toward those kinds of goals and outcomes. One is in the development of thin membranes that are highly flexible, sort of mechanically deformable with elastic mechanics to mechanical responses to large strain deformation. So sort of skin-like devices that can be integrated not only with the epidermis, but the surface of the brain, the heart, the kidneys, the peripheral nerves, as I mentioned before, but which are able to support really sophistication in electronic performance and biosensor operation that's comparable to what you would find in a more conventional platform technology built on a semiconductor wafer. So we're really trying to make electronics look more like biology from the standpoint of the physical form factors. That's one area. Another area is a little bit distinct from that, but heading in this overall direction of facilitated biointegration is in the development of electronic circuits and sensors that are built out of materials that are water soluble. That is, biocompatible and able to dissolve or disintegrate or otherwise disappear when immersed in biofluids over controlled time frames. And so you can think about those devices as temporary implants. So like resorbable sutures in a sense, conceptually, that is, they have lifetimes that are timed to a natural process such as wound healing, but in these cases with full electronic functionality, digital circuit capability, radio wave communication capacity, wireless energy harvesting strategies, and so on. And so we think we kind of know what how to do things in that space. And then a third area is a little bit more exploratory, but one that we think may evolve into something that could be interesting and powerful in a sense, and that is in the development of microsystems technologies that adopt the kind of open 3D framework type architectures that you see in biology in terms of neural networks, vascular trees at the cellular level, cytoskeletons, and thinking about how to sort of induce a geometric transformation from planar geometries and conventional circuits into these kind of open 3D network type architectures. And we think we know kind of how to do that. But I'm going to focus just on this first area, that is sort of skin-like devices. And what's the challenge? The challenge is really to recast, reformulate, the kinds of technologies that serve as the core foundations of consumer electronic gadgetry, industrial electronics, military systems, and so on, all of which are built on, monocrystalline semiconductor wafers, which is a spectacularly well-developed piece of materials technology, a great platform for doing sort of the photolithographic and other kinds of processing approaches that are needed to create circuits in the first place, but highly mismatched from the kinds of materials and structures and organs that you see in living systems. This is a highly planar, highly rigid, brittle type of technology built with lots of materials that are intrinsically incompatible with biological systems. Like, how do you go from that to something that you know, is more skin-like, you know, in its mechanical and physical properties? And one way might be to you know, throw out silicon and gallium arsenide and gallium nitride and develop, you know, polymer-based semiconductors and maybe carbon nanotube-based electronic circuits. And I think those are interesting directions from an academic research standpoint. And we've spent a lot of time looking at those kinds of possibilities, and we still have some level of effort, you know, in those directions in my group. But the other question you might think about, or the other path that you might contemplate, would be just to redeploy silicon in a non-wafer based format and heterogeneously integrate it with plastic or elastomer materials to achieve the same outcome, but in a way that could leverage all of the incredible scientific and engineering capabilities that exist around a material like silicon. And that's turned out to be the most effective approach for us, and it really represents the dominating theme of our research efforts in this broader area. And so what are the ideas? And this is really you know, a topic area that you know, is quite involved from an engineering standpoint. I'm just going to summarize it in like 2 slides. And so there's a lot of content here, and I'd be happy to answer questions if people are interested in some of the details. I just give a high level picture so I can focus on system level embodiments and deployments and you know, clinical needs that we're focused on these days. And so the approach is really twofold. It's really 2 really simple ideas, and it's just a recognition first that you know, the mechanical properties of any material are defined not only by the intrinsic you know, constitutive properties that characterize that material, but also the geometry of the material structure itself. And so a silicon wafer is rigid and brittle, partly because the silicon has those kinds of characteristics, but also because the wafer is fairly thick, maybe 0.5 millimeter or 1 millimeter in thickness. And for any material, if you make it sufficiently thin, it becomes mechanically flexible just by virtue of the fact that the bending stiffness scales with the cube of the thickness. And so if you create strategies that allow for you know, nano ribbons or nano membranes to be shaved off of the near surface region of a silicon wafer, you can create a form of silicon that's very flexible. Still silicon, it still offers the same electronic properties, can be thick enough to support the kind of transport characteristics that you need for a MOSFET, for example, but very, very flexible because of the extreme thin geometry. So maybe 100 nanometers in thickness might be a typical number compared to, you know, the millimeter thickness of the wafer. You're talking about 13, 14 orders of magnitude reduction in bending stiffness. And so that has a qualitative impact on the way you think about the material. The other thing about making a material thin is it means that you can minimize the bending-induced strains associated with bending to a given radius of curvature. So it not only reduces the flexural rigidity, but it increases the bendability before the onset of a fracture, which will occur at about a 1% tensile strain in silicon. So that becomes kind of interesting. And then you can think about these ribbons and membranes as building block materials you can you know, mount onto a flexible or a stretchable substrate, you know, to produce a system that has mechanics that begin to get closer to those associated with biological tissues. So that's idea number 1, but it doesn't really get you all the way there because a thin sheet of silicon is flexible, but it's not stretchable. Ultimately, you think about the brain or the heart, these are materials that are not only flexing, but they're actually undergoing large strain deformations as a result of pulsatile blood flow, as a result of the contraction of the cardiomyocytes and so on. And so you really need something that not only flexes, but stretches to accommodate those natural motions. And the way to get to stretchable is you take these thin ribbons and then you bond them to an underlying low modulus elastomeric substrate, such as a silicone-based polymer, but you bond them not in a flat geometry, in sort of a wavy shape. And with that kind of buccal geometry, you essentially embody the physics of an accordion bellows in the sense that you can stretch and twist and deform this kind of hard, soft material structure in a way that allows large end-to-end level deformations with elastic restoring forces associated with the substrate, but in a way that doesn't induce fracture, creating strains in the silicon itself, because these buckled geometries can change to accommodate the overall system level strain through changes in amplitude and wavelength. So that's pretty much it. You can exploit those kinds of ideas in very advanced engineering embodiments by sort of extending those concepts. And I won't go through the details, but just quickly. I mean, you can exploit out-of-plane buckling, but also in-plane buckling using filamentary serpentine geometries. You can connect all this stuff together, create this kind of engineered hard, soft, composite material structure with quantitative attention to the underlying mechanics, and begin to piece together overall systems that have these skin-like or epidermal-like physical characteristics. And by that, I mean effective moduli that are comparable to those of the skin, thicknesses comparable, again, rates of water permeation that are comparable to those associated with the stratum corneum, thermal mass loading that is similar to that of the skin itself. And so you think about it as a second skin, essentially intimately integrated to the surface of the natural skin, in such a way that that interface can be exploited for clinical grade measurements of underlying physiological processes by integrating appropriate electronics and biosensors into those kind of open network type of architectures, where you're equally paying equal attention to the circuit design and the mechanics design to realize these systems. And so this is kind of ancient history for us, and maybe many of you have seen these kinds of devices. Many groups are pursuing these kinds of technologies. We published that in 2011, felt like we had a good handle on how to do things, got a little bit better in 2014. And then from that point on, we've really focused on what is this kind of technology good for, in parallel with continued development of the foundational capabilities, trying to identify ways that these technologies could be of benefit to patients. And that's kind of where we pivoted, starting around 2015 or so. And it really motivated the move from University of Illinois to Northwestern so that we could more intimately couple ourselves into a medical community here in Chicago. And so this is a finite element model of one of these types of devices at the system level, just to give you a sense that circuit design is important, but you also have to pay equal attention to the mechanics designs associated with the layouts, and you have to do all the optimization to figure out what's going on and how you can configure chips and interconnects and so on to achieve these skin-like properties. And a lot of this work is done with a faculty member here, theoretical mechanician, Young Huang, and so he runs these kinds of simulations. Turn out to be a critical component of engineering design for these kinds of systems. So that's kind of how it works. That skin interface is very important. You think about your fidelity and measurement. You want a very low impedance associated with the contact, and that could be thermal impedance, electrical impedance, even fluidic impedance, and that's really driven by intimate contact. And the surface of the skin is highly rough and textured, and kind of how you do that turns out to be really important. And so these kind of filamentary serpentine constructs not only give you the mechanics that you want, but also the geometric conformability to these textured biological surfaces. And that's kind of illustrated here in this colorized SEM view of a mesh structure of this type resting against a polymer replica of human skin. So that's what it looks like. If you put it all together, now you can begin to do clinical grade measurements outside of the clinic in these skin-like forms continuously and wirelessly. And I will go through the details, but there's probably 50 different types of sensors, and we publish lots of papers in this area. A lot of other groups as well. They make great contributions and ideas of their own and so on. But you can do ECG, not just heart rate, but full ECG. You can measure hydration. You can do tonometry, so pressure, pulse wave dynamics associated with blood flow through near surface arteries, all sorts of things that demand physical contact with the skin, currently only done in clinical or laboratory settings. Now you can think about these kinds of measurements continuously, not episodically, but really kind of continuously, yielding tremendous depth of information and potential insights that could be useful for a physician to determine trajectory of care for an individual patient. So as I mentioned, there's a whole portfolio of different types of biosensors that are compatible with these skin-like platforms. I'm not going to go into it, but all kinds of thermal sensors, electrical, I'll come back to fluidic, a little bit mechanical, optical, mechanoacoustic, so you can sort of capture signals that are very comparable to those associated with a stethoscope, but now in a skin-like form continuously. All of these things are now possible. And so, like I said, we really had a chance to dig into engineering these systems to address specific unmet clinical needs. And we're very excited about opportunities in maternal, fetal, neonatal, and pediatric health, because I think those classes of patients could most strongly benefit from a wireless skin-like, highly non-invasive, almost imperceptible monitoring technology. And I'll give you a sense of what we're doing in neonates, but we have active programs in all of those other areas that I just mentioned. And so you think about a premature baby and what how they're cared for in a hospital setting today. If you take a look at what's going on in a neonatal intensive care unit, you'll see a rat's nest of wires, adhesive tapes, rigid biosensors coupled to the skin of these babies to monitor full vital signs continuously, because they're in a fragile health status. You almost have to do that so that if they enter a critical stage, then nurses and physicians, neonatologists can engage very quickly. The problem is that this is highly non-ideal, as you might imagine, for these tiny babies to be wired up in this way. Whole host of clinical challenges follow from that. And so in about 2015, we decided, if these skin-like devices really worked as we had hoped they could work, we'd use them on these patients, get rid of all this stuff, and replace it with 2 or 3 of these patches. And it seemed like something that would be feasible. We had no idea how challenging that would be. It was almost a 5-year effort to get it done, but we're able to make that happen. And I won't go into the details. Again, more than happy to discuss it. If people are interested, either in the Q&A period, or you can feel free to send me an email afterward. But we're able to do that with 2 of these epidermal electronic systems. One goes on the chest, illustrated here, the other one on the limb, typically the foot, to recapitulate all of the vital signs measurements that are done with wired technologies today, even in the most sophisticated level 4 NICUs that you see here in Chicago, for example. And we published this about one year ago. So the device on the chest, like I said, it's providing capability in continuous ECG monitoring. It's wireless, it's battery-free, through wireless power transfer and then wireless data communication continuously to capture full ECG and also skin temperature from the surface of the chest. And in all the studies that we've done on neonates in operating NICUs, we've had the wired systems in place as well. So that allows us to do a quantitative validation of the precision, the noise level, the reliability of these wireless devices, and they match up quite nicely. So for the device on the chest, you're getting heart rate variability, you get respiration rate from the periodic change in the depth of the R peak in the ECG, and you're getting a skin temperature measurement. But that's not everything. You also need blood oxygenation. And so we use a separate device, an optoelectronic device for that measurement. And this is another battery-free wireless skin-like platform, but in this case, it's a pair of LEDs flashing on and off out of phase, and an integrated photodetector that's measuring backscattered light after interaction with the skin. And so wireless transmission from that photodiode yields a photoplasmography signal from which blood oxygenation, SpO2, can be determined. So you put all that together, it works. This is an example of that chest unit on a baby in Lurie Children's Hospital here in Chicago. This is the 31-week-old premature baby. The hand on the right hand side of the image there, that's Aaron Hambas. He's head of neonatology at Lurie's. You can see the wire-based systems that are simultaneously capturing ECG to allow validation of the technology. I think we've done about 150 babies at this point, no adverse events, and the technology looks very solid. We've also expanded out beyond the NICU. As I mentioned, we're interested in pediatric patients, so we have devices deployed in the PICU, pediatric intensive care unit. There, eliminating wires is also important. It really facilitates parent-child interactions, as illustrated here. So you can see the device on the chest, one on the foot. Here, the wireless antenna that's transmitting power to these devices and also receiving data from them is mounted in the base of the chair. And so it really allows for freedom of motion and more intimate, more frequent engagement between the baby and the parent. And that's very important from a therapeutic standpoint of the healthy development of the baby at this stage of their lives. So that's how it works. So as I mentioned, we published this last year. It was a nice outcome of a long slog to get all of these pieces working. I would just mention, if you want to be active in this area and you really want to do things at a meaningful level, I think it really demands interdisciplinary engagement between engineers and medical professionals. And this was almost unwieldy in terms of the collaboration, but I think you needed all these pieces to come together, really all areas of engineering science and corresponding expertise in medicine, dermatology, neonatology, and pediatrics, and various other folks, nurses in particular, very, very important here. So that's what's going on. Shortly after that, we were approached by the Bill and Melinda Gates Foundation, the Save the Children Foundation, to think about deploying those technologies in lower and middle income countries, in particular in Africa, where there's really no monitoring technology at all. And so we really had to take a look at the cost structure, the deployability, the designs of these devices, had to modify a few things. We ended up publishing the latest versions of these platforms in Nature Medicine just a few months ago. But this is a deployable, cost-effective version of what I just described to you. And we're currently deployed in Africa, in Zambia, Kenya, and Ghana. I spent a few weeks in Zambia myself in December. It's quite touching to see, how these devices, have the potential to really improve the way that, babies are cared for in those parts of the world. And the vision here is for them to just leapfrog the old style wired-based systems, just go straight to wireless, and I think it makes a lot of sense. The fidelity is much better. It's much more patient friendly. And by analogy, I think it makes a lot of sense. They also, leapfrog landline based telecommunication technology straight to cell phones. And I think the same model could play out here. So currently we're in 17 countries and 5 continents, and we'll touch roughly 10,000 patients by the end of the year. We did our first FDA submission last month, and we'll see how that goes. But I expect to get that we'll get approval within the next 60 days, and that will really greatly expand our ability to get these into the field. And so I think the excitement, at least from our standpoint, is now you have a basic framework that seems to function. It seems to have the right cost structure and the right level of deployability. Now you can think about all kinds of new use cases, new sensor opportunities that can be dropped into those platforms. And so we have devices for monitoring in the OR. We have devices on Parkinson's patients with funding from Michael J. Fox Foundation. We're looking at applications in stroke rehabilitation, particularly around dysphagia and aphasia. As I mentioned before, maternal fetal, very high interest level for us. And we have devices for those applications also into Africa and separately funded programs with the Gates Foundation. So lots of things in the pipeline. Doing flow monitoring for shunts for hydrocephalus patients. We have pediatric near systems, as I mentioned before, fetal ECG, that works. We have devices on stroke patients, as I mentioned, aphasia, dysphagia. We have neonatal EEG capabilities, and we're using devices to monitor surgical recovery in pediatric patients also here in Lurie Children's Hospital. So with that, let me spend the last 10 minutes on a more recent platform that uses this same concept of skin-like devices coupled to the body for monitoring of health-related parameters, but really thinking about opportunities beyond what you can do with electronic sensors. So beyond electronics and thermal and physics-based measurements, I guess optical, thinking about biomarkers and biofluids and biochemistry, to kind of qualitatively expand what's possible. And we're kind of asking the question, can you reformulate lab-on-a-chip type technologies to be skin-like in the same way that you can electronics technologies to have that kind of biocompatible physical property. And it turns out that you can do that. It's actually not that hard. I'm actually surprised that people haven't looked at this before. But anyway, we published a paper in 2016 whereby we basically created soft skin-like microfluidic networks with valves and reservoirs and adhesive coupling interfaces to the underlying skin, with the idea of capturing sweat and using sweat as an unusual and highly underexplored but maybe interesting class of biofluid that can complement blood and interstitial fluid, with the main advantage of the ability for non-invasive collection. And the platforms are based on silicone materials, soft lithographic techniques for forming the microfluidic platforms, and then biocompatible elastomeric adhesives, dual layer adhesives, to couple that microfluidic technology to the skin, where openings in the adhesives allow sweat glands in those corresponding locations to deliver sweat up into inlet ports in the back side of these microfluidic structures, where the eccrine glands actually serve as the pumping mechanism for driving fluid flow through various parts of these devices. It could be routed around in different reservoirs through different microfluidic channel structures, such that either electrochemical approaches could be used to sort of analyze the sweat, or what we like to do is use colorimetric chemical reagents to kind of totally eliminate the need for electronics and power supply and the rest of it to allow sort of sophisticated in situ capture, storage, and biomarker analysis of sweat. And that's kind of what we've been focused on. And so sweat is kind of interesting. I mean, it's been used in the past in medical context, primarily for screening for cystic fibrosis. High chloride levels are known as an indicator of CF, and that's done routinely in a hospital, but with kind of primitive technologies, basically coiled up tubes and hockey puck type fixtures that get strapped tightly to the arms of pediatric patients for collection of sweat, and then the tubes are uncoiled and the sweat is extracted, and the analysis is done with a benchtop analytical equipment, or you use an adhesive pad just taped to the surface of the skin, and you wring the pad out to extract the sweat for chemical analysis. But in 2016, a couple of other groups, in addition to ours, were beginning to think about skin interface devices. One at Berkeley, one at SNU. Great work out of University of Cincinnati, predating that. But those approaches are not based on microfluidics. It's based on skin interface electrochemical sensors, and those are great approaches. But they don't allow, for example, for measurements of sweat loss or sweat rate, because there's no microfluidic functionality embedded. And they don't kind of leverage all the amazing microfluidic technologies that have emerged from that lab on a chip community over the last 20, 30 years. So that's kind of a point of differentiation around what we're doing compared to these other groups. But anyway, this is the first platform just to demonstrate the capabilities here. This one has 5 inlets. 4 of those inlets connect to these circular reservoirs. Each one of those reservoirs is filled with a colorimetric chemical assay. In this case, for lactate, chloride, glucose, and pH. So you can make those kinds of assessments in terms of the chemistry of sweat. The 5th inlet connects to a narrow microfluidic channel that terminates in this wider serpentine channel structure that runs around the perimeter of the device and is filled with a cobalt chloride hydrogel that changes in color from purple to red upon reaction with water. And so just by visually inspecting this device, from color change, you can determine these biomarker concentrations, but you can also determine the local sweat loss, and from measurements at 2 time points, the sweat rate, based on the geometry of the channel, the size of the inlet, and so on. And so that turns out to be fairly important for reasons that I'll describe in a few minutes. But as with the electronics, the mechanics are critically important here, maybe even more important, because now you need a device that not only adheres to the skin, but forms a watertight seal in the context of what could be profuse sweating. And the way that you do that is you use a robust adhesive, obviously, but the other way that you approach it from a mechanical engineering standpoint is you make the devices as thin and soft as possible, because that reduces the interface stresses at the contacting interface with the skin. So as with the electronics, with these microfluidic systems, we're guided by quantitative 3D finite element modeling of the mechanics. In this case, the mechanics of not only microfluidics, but an integrated antenna structure for near field communication. But this becomes an important aspect of our material science development and the device architecture optimization as well. So this is what one of these devices look like. Adhere to the surface of the skin. You can see that serpentine channel filled up to this point, sort of the 7 o'clock position, perhaps. And by calibration, by knowing the geometry here, you can determine how much sweat was lost locally at that part of the skin. And it turns out that you can do a pretty good job of calibrating local measurement of sweat loss to full body loss, which is very important in terms of managing hydration in the context of athletic competition, for example. I'll come back to that in a little bit. But we're also we've also filled these 4 reservoirs for biomarker analysis of sweat as well. But these devices really provides a real-time visual indication of sweat dynamics. And this is an example of a device, a slightly different channel geometry and a slightly different approach to visualization, where instead of that cobalt chloride material, we just use a colored dye located at the inlet. And in this case, a sort of serpentine channel, zigzag channel along the length of the device. But you can see at various time points during my workout, I can just visualize, okay, how much sweat loss has occurred up to that time. It's very easy to do that. And, it's revealing, because if you look at adjacent regions of my skin next to the patch, you don't see really any accumulation of sweat. That's because the sweat is evaporating continuously. And so you lose track of how much sweat loss you've actually suffered at any given point during the workout, whereas this device provides very highly quantitative means for providing that feedback. And one interesting thing of this, you can look at the cumulative sweat loss by looking at the fill front position in this device as a function of exercise duration, and you fit a line to that. Once I'm up and running, I mean, my sweat glands are, releasing sweat at an amazingly fixed rate to within the uncertainties. I mean, within, I don't know, like 1%, they're running like clockwork. It's pretty incredible. I don't think that's ever been measured before. So anyway, just kind of an interesting anecdote about, body chemistry and body processes is a really highly controlled rate of sweating in this case. But then, the interest in the material science and the chemistry is like how many different biomarkers in sweat can you detect with colorimetric chemical reagents? What are the range of possibilities? About a dozen that we published over the last 2-3 years, and I'll just very quickly step you through a few representative ones. So we use this silver chloroanalate for measuring chloride in sweat, which is pretty much electrostatically balanced with sodium. There's a little bit of potassium in sweat, but if you measure chloride in sweat, that's a good indication of electrolyte concentration. And as I mentioned before, chloride is a marker for CF. I'll come back to that in a little bit. But with an appropriate formulation of silver chloroanalate, you can get a really robust color change over a physiologically relevant range of concentrations of chloride. And this is what it looks like. It allows a very precise measurement, in situ measurement of chloride concentration without any electronics. You can do glucose. It's a little bit more complicated. It's enzymatic, but you can do that. You can do lactate, again, enzymatic based reaction, allow you to do lactate over physiologically relevant range of concentrations in sweat. pH is super easy. You can do that as well. You put it all together and you can make sophisticated sort of multimodal devices that don't require any kind of power source, any kind of electronics. This is one of the more sophisticated devices of that type that we built. And we can build in passive valves and so on, and we'll get into details there. I'm running out of time a little bit, but you can check out the details in this ACS sensors paper from last year if you're interested. So in terms of commercial opportunities in deployment, I mentioned sort of the Gates Foundation activities in Africa. Here for this device, we're also moving it out of an academic lab setting, in this case, in a partnership with Gatorade. And so they make sports beverages, and they're very interested in precision hydration management for athletes. And so the idea is, if you go into a competition well hydrated, you'd like to be able to measure exactly how much sweat you've lost at any given point, so you know exactly how much water you need to drink to bring you back to that optimal hydration state. And so this patch actually does that visually, just by looking at the extent of filling of these channels and understanding the correlation between local and full body loss. But we also have this chloroanalate-based channel down here, so it allows the user of the device to determine not only sweat loss, but electrolyte loss through electrolyte concentration plus sweat loss. And Gatorade's products are electrolyte replenishing as well, and they can be tailored in terms of electrolyte concentration to individual body chemistry. So everybody has a different electrolyte level in their sweat. This patch allows users of the device to determine not only how much Gatorade they need to drink, but what formulation of Gatorade matches their body chemistry. So this has been a great collaboration and a great driver, I think, for developing the technology out for the sorts of medical applications that we're ultimately interested in. So we've done probably 1,500, 2,000 subjects, many elite athletes with Gatorade, and we've been able to establish very high levels of accuracy of these kinds of devices relative to the standard, which is absorbent pad and HPLC measurements of sweat loss and chloride concentration respectively. And so you see some scatter here. I mean, this is biology, and we're not collecting sweat from exactly the same regions of the body, but this is the kind of correlation that that people are happy with. And so we've done a lot with the Gatorade Sports Science Institute. We've done field trials on youth athletes, professional athletes. This is IMG Academy in Florida, and the devices work very well. And there's a commercial campaign out now. This is Serena Williams wearing one of the devices. This is Paul George. He's a starting forward for the LA Clippers in the NBA. And this is looking very exciting. I think we'll do 100,000 devices through the end of the year, and probably on the order of 1 million next year with a broader commercial launch. So very low cost device, just providing some insights into sweat loss and electrolyte loss. But let me just conclude the last 2 minutes with orientation around what might be possible from the standpoint of medical diagnostics with these devices. That's where we're ultimately interested. And I mentioned the CF screening, and we were contacted by people at Lurie Children's Hospital who do this kind of screening on a regular basis. It works to some degree. The problem is you get sample insufficient, not sufficient failure. So failure rates associated with leakage of sweat around this kind of puck-based device. And they asked us if we could build one of our soft sort of skin sticker-based microfluidic devices, not only to eliminate that leakage, but also to eliminate the need for use of benchtop analytical instrumentation and separate analysis of chloride. To be able to do that in situ would greatly facilitate the test. And so we're able to put together devices with that kind of functionality. They turn out to work very well. It's very simple. It's just a soft adhesive interface to the skin. You capture the sweat. You got the chloranolate analysis capability built into the patch, so you don't have to worry about loss of sweat during transfer to a separate analytical instrument. And this looks like maybe an initial application in as a medical diagnostic. And so we've probably done 50 patients so far, and it's looking quite good. We're typically collecting significantly more sweat, and again, we do in situ analysis, greatly facilitate the process, and actually allow it to be done in the home, which is going to be really interesting and super convenient for patients. So that's showing some of the data correlation. So with that, I'll conclude. So I described skin interface electronics, microfluidics, a lot of opportunities for additional research in these areas. I think there are a lot of ways for many groups to contribute its technologies with broad societal benefits, and I think it's a great area for research these days, and will likely be a growing area into the future. So I'll acknowledge the senior collaborators, many collaborators here, as I pointed out as we move through the talk. But the students, the postdocs are the most important folks. They do all the work. And so I'll just conclude by acknowledging them for their great ideas and their dedication to this sort of research. So thank you again for your attention.
Thank you very much, John, for this wonderful talk. We have lots of questions coming in. And what I'm trying to do is I will try to club some of these questions. I can see some questions are on electronics, some are related to sweat, some are related to reliability of these structures. There's a question related to power management, and then NFC, etc. So first question is by Emre from ARM, and he's asking, is it possible to develop silicon nanoribbons with sub-micron channel lengths?
Yes, actually, a lot of what we do is to sort of leverage, I guess, state-of-the-art processing capabilities that exist for silicon wafer-based technologies. So the ribbons are not produced and then subsequently processed. All the processing typically happens on the wafer, and then the undercut and the release in the form of either ribbons or very thin chiplets or other kinds of geometries are done as a final step. And so we've even demonstrated that you can do this kind of thing with foundry-based SOI technology. We have a collaboration with XFAB International, and they have an SOI process that we've used. And in those cases, we are typically releasing the CMOS from the surface of the wafer, either by selectively eliminating the box layer and lifting off in that way, or we can etch all the way through the box layer, and then we do anisotropic undercut etching of the handle wafer. And in that case, we lift off the CMOS with the box layer integrated on the back side. So you end up with very, very thin silicon CMOS circuits. So not even individual transistors, but collections of them in small blocks. And in that way, you can use state-of-the-art, lithography, the latest, design node, kind of whatever you want to do is possible. So I think that probably answers the question. And maybe part of the confusion is that, in this presentation, I was describing things at such a high level, it didn't kind of get into the nitty-gritty of how it works. But the idea is thin geometries and flexible mechanics, and then you kind of move from there in terms of the controlled buckling. But hopefully that answers the question.
Okay, thanks, John. Next question is by Faisal Chaudhary, and a related question also by Benjamin Sitkus. So the question is about reliability. So they're asking, can you comment about accuracy, reliability, medical certificate requirement, and high volume cost of manufacturing opportunities for such devices? Related was Benjamin was asking about reliability or robustness of stretchable devices.
Yeah, so start with robustness, and then I'll say something about reliability and cost. So a couple of things. I mentioned that we do a lot of, well, our collaborators do a lot of quantitative finite element modeling analysis, and that's critical not only for achieving the kind of effective modulus, in a sense, that you ultimately want for a non-invasive integration and a matching of modulus to the point of integration on the skin or other organs of the body, but it also allows us to determine when we expect to begin to see fatigue in the actual functional materials associated with repeated cycles of stretching or bending or twisting. And so we have the capacity then up front to engineer the device structures and the layout such that the peak strains that are experienced by the functional materials, typically the copper wiring is what we have to pay attention to, because fatigue and plastic deformation will set in at about 0.2, 0.3% tensile strain in most metals. And you design the system so that at the maximum level of stretch that you expect to see for a given application, that could be defined by the point of integration and natural motions that are inducing deformations, or it could be related to the degree of bending that's needed to mount the device on a curved body part, or it could be a combination of those things. How do you design the layouts to avoid maximum strains in the functional materials that would otherwise begin to lead to fatigue or reliability problems? So all of it is designed in upfront from quantitative engineering. So again, got to worry about circuit design, but now you have to really worry about mechanics design. And I guess in conventional integrated circuit technology, you do have to worry about mechanics as well, but not at this extreme level. So you do that, you design it in upfront, and then we have all kinds of like cyclical testing rigs for stretch, for twist, for bending, and we typically do 100,000 cycles or something like that. I mean, I think you may be thinking about a 3-year lifetime, and maybe depending on the use case, you kind of estimate how many cycles are gonna be needed, and that's kind of the way that we do it. The additional point there is that these devices can all be overstretched. There's nothing intrinsically, at least in the designs that I've shown, that strain limit the system. So you can design it to accommodate a stretch of say 20%, but that's not and that may be fine for use after the device is integrated onto the patient. But in terms of real world reliability, that doesn't guarantee that the nurse won't stretch it to 50% when they're manipulating the device, right? And so there are various ways to incorporate strain limiting fabrics, super thin, super low modulus, but it provides that J-shaped stress strain curve that you ultimately need to have that sort of mechanical limiter functionality. So we published a couple of papers on that type of scheme, and in a lot of cases we do incorporate very thin fabrics. I mean, these are the kinds of things you have to worry about you going into Africa. Not that these people don't know how to use the devices, but they're you're talking about robustness at a level that goes beyond kind of what you need to worry about when you're working directly with your collaborators here down the street in Chicago. So those are some of the considerations, not all of them, but some of the considerations. The costs. One of the things that we had to do with the Gates is you have to pass a cost due diligence process, because they're not interested in technologies that can't be scaled to very low cost. And you think about it in terms of a cost per patient per day. And you need to get in the range of a couple of cents or less to be viable. That is a cost of a per patient day of monitoring. So the devices involve reusability, right? And so you have to go through that. And in order to get there, you really have to be able to tap into and leverage embedded manufacturing infrastructure that already exists for consumer electronics gadgetry. If you don't do that, it's very, very difficult, because then you have to develop specialized tooling and unproven scaled manufacturing capabilities. So for that Nature Medicine paper, a lot of the work was around how do we take those very advanced sort of bleeding edge battery-free systems that I described and morph them into something that aligns with manufacturing capabilities that we can tap into with external partners. So a lot of that, work was focused on that engineering aspect. And so you can get down into those cost regimes, a few cents, small numbers of cents, so like 2-3 cents per patient day. And that seemed to be kind of where the Gates Foundation folks felt, and the Save the Children Foundation folks felt that you needed to be. And then we move forward on that basis. I think those are the main questions. Is that right?
Yes, that's right, John. So next question, John, is related to the communication of various patches that you've shown in the presentation, and this comes from Pablo Escobedo from University of Glasgow. So he's saying that you are using NFC, but NFC has a problem of, it's a limitation that it can be a short distance communication range. So the question then is this a limitation for continuous monitoring, especially for neonatal care? And have you considered other wireless technologies such as UHF instead of HF?
Yeah, so we have some electrical engineering expertise in my group. I suspect many in the audience have deeper expertise in EE and wireless. But so having said that, the first devices that we deployed and published did in fact use NFC, and we do a lot with NFC. I mean, we like it because you can operate without a battery. In many cases, we don't need high data rate. And so it's great, and it's safe in the sense that you're operating in an HF frequency range where there's very little to negligible absorption by water or biofluids, and so you don't have the same kind of exposure thresholds and SARS type issues you have to think about at higher frequencies. So NFC is great in a lot of ways, and there's a huge technology base supporting, NFC and phones and RFID tags, and, it's great. But as was pointed out, there is a limited range, but it's not too bad. I mean, we get about a half a meter, maybe a meter, if we're kind of aggressive around the antenna design. So if you think about neonate, it's a very small patient, and they're not running around. I mean, they're in an isolate. It's a very well-defined space. And so we put an antenna in the base of the isolate. We really capture the whole volume of interest. And there are other applications in the hospital setting where that same approach is going to work fine. So for a patient who's in a wheelchair, you put it in the base of the wheelchair, you're pretty much good. Or, if you're in an adult ICU, patients are in the bed mostly. And so you put it in the mattress under the bed. We've done all of those things. So I wouldn't discount it. I mean, I think NFC is a very powerful option for certain instances, but as was suggested by the question, it's not going to address all requirements. And so for other use cases, so for the Africa deployment, we decided against NFC because it required a reader. So it's just another piece of hardware that we're going to have to deal with. And the antenna, it's straightforward, but then you need the RF power supply. You need some other electronics to get, an interface to a PC, and getting to a cell phone is not straightforward. I mean, it's doable, but then it's just additional complexity. And for LMICs, I think everyone has a cell phone, and most people even have access to tablets. And if you can use the cell phone or the tablet in a very direct way, then you eliminate all the overhead costs associated with the externalized electronics and the monitoring equipment. And so for the Nature Medicine paper and the devices into Africa, everything is Bluetooth. Again, it's a cost consideration. It's a simplicity in terms of components and engineering at the system level. And it's a compatibility with smartphones and long-range operation. because for them to install, NFC antennas into each of the, the isolates and the structures that they have, it's going to be really cumbersome. It's going to be really hard to do that. So if you can do, 50 meters instead of 50 centimeters, it really opens things up. You have one tablet and you're monitoring 30 babies, something like that, across an entire space. And in terms of resource deployment, that's probably the greatest value of these monitoring technologies in those parts of the world, because what they lack are trained healthcare workers. And so you want each worker to be fully leveraged to the maximum extent possible. And so you get one nurse being able to oversee 30, 50 babies. That's very powerful. And it's really only possible if you have continuous monitoring and alerts so that they can focus on patients in greatest need. So that's the model, and that's the communication strategy that we're using. You could think about others, but I think Bluetooth NFC, because they're so strongly aligned with consumer gadgets, that you get the cost benefit, you get the deployability. It seemed to be a good choice for us, but I don't know. I mean, maybe other people have better ideas, different approaches. I'm fully aware that maybe there are other ways, and so but those are the considerations around our choices.
Well, thanks again, John. The next category of questions, again, I'm clubbing because questions are coming in, and we have several questions. It would be difficult to take up all of them. So what I'll do is, after this session, I'll send these questions to you, also a set of these questions. So next set of question is related to sensors and biocompatibility, as well as attaching to the skin. How do you attach the sensors to the skin? So question from Nunzia Molinaro: what about the possibility of using this technology for monitoring joint movements? Then question from Suksmandira Harimurthy, asking about what is the potential of using epidermal electronics for fetal sign monitoring. And then another question coming from Nunzia Molinaro about how do you attach polymeric substrate to the skin? So these are questions about sensors. And there's another question about biocompatibility from M. Ilyas, asking about biocompatibility of substrate material.
Yeah, those are all great questions. So in terms of the adhesive interfaces of the skin, because these devices are very thin, they're very soft, you don't need a very strong adhesive to keep the devices coupled to the skin. That's one point to make. The other thing is that the skin in these neonates is very underdeveloped. It's very, very fragile. You don't want to be messing around with novel skin adhesives. I think that's a whole long research and regulatory effort in itself. And so we've tried to use very slightly modified formulations of existing FDA-approved skin adhesives for neonates. So in many cases, it's very lightly adhesive hydrogels that provides a conductive interface. It isolates the electronics entirely. We don't have a direct metal skin interface anymore. It's metal hydrogel skin. And so that tends to be, the best approach, and that's what we're doing. So the adhesives become single use, and the devices themselves are multi-use, and that also facilitates sterilization and cleaning, and it just kind of isolates things. It tends to be the best type of approach. I don't know, that captured answer, I think, to several of those questions, but maybe not all of them. I don't know what the other.
Well, one was related to biocompatibility of the substrate itself.
Yeah, so I think so we try to stick with materials like gold for metals. We use FDA approved silicone elastomers as the packaging materials or the encapsulating substrate and the superstrate. And then at that point, the electronic materials themselves is less critical because they're not directly engaging with the patient in any way. It's really just the metal, the hydrogel, and the silicone elastomer, and they're all approved materials. There may be opportunities for novel materials and doing things in that space, but we haven't spent a lot of time on that because what we have seems to work pretty well. And like I said, I think our focus really is on deployment and get things out of the lab at some level. But that's not to say there aren't opportunities for looking at new materials, but that's been kind of our focus over the last few years.
All right, so there's a next question which is related to sweat, John, and this is from Hamdi Torun, and it says that there are several biomarkers identified to be present in sweat. However, the measured levels should be interpreted in terms of their presence in blood, and this is sometimes debatable. So he's expecting some comments from you about that. And which application do you think is the most promising for sweat analysis?
Yeah, great question. I think it's a very valid question. I think Gatorade doesn't care how it correlates to blood. So there are some immediate and the CF screening, correlation to blood. It's, maybe it's interesting, but they've already figured it out. And, so I would say the point there is that there is well-defined value in sweat analytics already without needing to figure out the correlations to blood. Now, the frontier and the opportunity areas are in biomarker analysis and sweat that tells you something about blood, because there's much deeper base of understanding of blood chemistry and a very shallow level of understanding of sweat chemistry. So I fully acknowledge the question. I think it's a hugely valuable direction for research to establish those correlations. But even now, there's already plenty of applications for sweat as it's known currently in terms of significance of sweat chemistry to body health, I guess. So we're by no means the only group in studying sweat. I mean, there are a lot of great groups. I highlighted a few of them. There are others as well. Wei Gao at Caltech, for example, is doing great work. So I'll just give you a few. So alcohol, sweat alcohol is known to correlate very nicely with blood alcohol. There's a very good correspondence there. Glucose, that's probably still a controversial topic. I don't know if I have a strong opinion on it. Probably there's a loose correlation. I don't think it's tight. It's probably not quantitative. I don't think you're going to be able to use sweat glucose as an alternative to blood glucose for diabetics and so on, and insulin delivery. I don't see that happening. But as a loose correlate, probably it's valuable at some level. We've begun to look at creatinine and urea in the context of kidney disorders. So you can pick up those biomarkers in sweat. I think it's an open question of how well they correlate to blood, but it's an active area of research for us. Lactate as well. I think there's probably some opportunities there. But we're deep into a comprehensive patient-based study cohort of 50 subjects where we're going to be doing full blood work. Well, we are doing full blood work and then full sweat analysis to try to answer these questions, because they're great questions. But I would say even if some of these correlations don't pan out, sweat's still interesting for us for the reasons that I mentioned before. But I think it's a great area for research, quite frankly. And it's not super easy because in these kinds of topics, you need statistically relevant numbers of patients. Blood work is not easy. You got to get patients who are willing not only to do the blood work, but they're also willing to hop on an exercise bike or jump in a sauna and sweat. So it's not trivial, and I think that's probably one of the reasons why there isn't a deeper literature on sweat. The other thing that's sweat chemistry. The other thing that's changed is through our work and others as well, there are now methods to capture pristine, well-controlled volumes of sweat. I think previously with the absorbent pads, and they have tools that you can scrape sweat off the surface of the skin, it's really not, amenable to any kind of detailed quantitative analysis of sweat chemistry. So I think a number of things are changing, and probably over the next, year, 2 years, 3 years, there's going to be a lot of clarity around the information content in sweat chemistry, but it's not really there yet. So it's a great question, and it's very much a topic of research interest for us.
Well, thanks again, John. We are running out of time. If you are still available, I can take up some more questions. There is one question on energy management, some questions related to electronics, but if not, then we can close the session at this point. So it's just your availability which will determine whether we continue, for how long we continue.
I can hang out as long as you want. I don't know what the schedule is like for something else.
So in that case, thanks a lot. In that case, I'll take up two more questions, and one is related to power management. It's coming from Dayalan from University of Glasgow, and he's asking how is the power management working for epidermal electronics? Do you see issues related to heating?
Yeah, so we've looked at that, and if you take a look at the paper we published last year, there's a tremendous amount of information on on heating. These are pretty low power devices. I think the NFC systems, like the steady state power consumptions, are probably kind of at a milliwatt level, and you know, the amount of power that's dissipated is somewhat distributed. So we haven't seen anything. We've done detailed measurements of changes in temperature. We have IR thermography results. Like I said, you can take a look at the paper. Supplemental information has a lot of content on that question, but very important because you know, the thermal budget, it's narrow, very narrow, because you know, the skin, you know, you heat it by more than, I don't know, 10 degrees Celsius for a certain amount of time, you're burning the skin, and you know, the skin on these neonates is even more fragile than that. So you probably have maybe 2-3 degrees at most, you know, in terms of your thermal budget. So you have to think about that, but it hasn't been a topic that we've had to grapple with a lot because the devices themselves are low power. I think what we worry about more in terms of thermal has to do with battery failure. So the Nature Medicine paper, the devices deployed into Africa, and also here at Lurie Children's, not just Africa. We've kind of transitioned, you know, many of our studies, not all of them, but many of them, the Bluetooth platform. You have a, you know, battery there, and for startup, you know, the Bluetooth is running about 10 to 15, maybe 12 milliwatts, and then it drops down after that startup phase. So the battery capacity needs to support 24-hour operation. That's just the clinical cadence. So you're talking about, you know, a battery capacity, I don't know, 30 milliamp hours or something like that. And then you have to worry, you know, concern yourself, not due to thermal associated with operation of the device. We really haven't seen any kind of significant heating, but what happens if the battery fails? Or like, what are the power management circuits? What are the protection circuits that you embed? So we have redundancy around battery shut off if there's any kind. So they're embedded temperature sensors in the devices themselves that are not configured to measure the body temperature, but configured to measure the temperature of the hottest components of the circuit, shut it down automatically if there's any kind of overheating. But you know, I think any kind of like skin coupled device, you know, you really have to think about safety at a whole nother level. It's not packaged, you know, like in a tight enclosure like an Apple Watch that's like loosely coupled to the body. This is something that's really intimate on the skin, and so we've done a lot, you know, in that space, and we've even, you know, run devices where we intentionally short out the battery, and then we watch what happens, and we sort of monitor the temperatures exactly and the kinetics, the time constants of when the battery protection circuit kicks in and shuts the system down. And we've done a lot along those lines. So probably end up publishing those results. We haven't done that yet, but it's a little bit more industrial type research, product development type research, but still very important. And then we also have kind of packaging strategies that optimize thermal isolation of the battery from the underlying skin, things like that. But it's a very, very important question, a very important topic. We've looked at it and thought about it. But again, you know, it's a new area of technology. I think probably there are a lot of good ideas out there in the broader community. And for any of these skin interface devices, you got to be pretty sophisticated on safety, you know, and that's one aspect of it, thermal.
Right. John, there is a question again from Emery, and this question is stretching from one patch to body sensor network. So the question is, do you foresee that multiple skin patches on a person's body can communicate with each other through the body, for example, body communication? And if you do, what are the challenges?
Yeah, I think that's a topic that other groups have looked at. I've been really interested in kind of following research in that space. I think it's very fascinating. We haven't done anything ourselves, but I think there are huge opportunities in thinking about those kind of body area networks, I guess. We do have, having said that, we do have programs where we have multiple devices. I mean, even the neonatal devices I talked about, it's binodal system, and those systems are time locked. So we have time synchronization strategies that get good timing down to a fraction of a millisecond. That's important because we're measuring hemodynamics, we're measuring pulse wave velocity and things like that. So they have to be time locked in order to capture data of that sort. But there's no communication through the body. It's all wireless between the devices and then wireless to an external reader. So that's kind of been our approach, is to allow the devices to communicate with one another, but not necessarily through the body. I'm not sure. I don't know. Probably others have deeper insights into this. What the advantage of through body versus through air communication is, but definitely there's a lot of value in synchronization and communication across multiple devices. And one example, we have 10 devices monitoring full body motion, full kinematics in premature babies. Actually, coming back to that again, because asynchronous motions, certain types of general motor assessments are used to determine the risk of a baby for development of cerebral palsy. And you need to do those assessments at the very earliest time point when there's still brain plasticity, such that physical therapy could kind of address that CP condition. So the goal of those programs, it's funded at a very high level by the Ryan Family Foundation here in Chicago, but the goal is to allow those kinds of general motor assessments be done in a data-driven, automated way that doesn't require a trained neurologist, so that the assessments can be done in the home. And so you ship devices out to a parent, they mount them up, measure for some period of time, they ship them back, and then we do machine learning and full motion recapitulation, using the data streams. And there, to get the full body, you need 10, and they all have to be time synchronized. So yeah, I mean, I think there's huge value, not only in like multimodal functionality of an individual patch, but then multiple patches. Done that on stroke survivors as well, to sort of quantify spastic as opposed to voluntary motion. And there we're doing accelerometry, but EMG recordings as well, multiple patches across the body. Parkinson's is another example. Pick up early signs of tremors and thinking about strategic locations, multiple devices. It's a great question. I guess the only aspect of that question I don't have a definitive answer to is what's the advantage of through body versus through the air. And everything we're doing is through the air right now.
Right. One last set of questions. Actually, there are many, but one last set of questions is related to your experiences. And this question is coming from Suksmandira Harimurthy and from Andrew Clausen. So the first one is that you have been collaborating with diverse disciplines. So basically, what is the key strategy that, if there's any strategy that you would like to share? And Andrew is asking your experience in terms of technology transfer, and when do you think, when do you look to move technology from lab to startup?
Yeah, so the first question, we've been pretty good with collaborations. I'm not sure exactly why, but I'm pretty easy to work with, I'd say. There's like just a personality thing that is probably more important than most people suspect. I mean, I think it's interpersonal interactions, but I'm not sure I have any deep insights into the psychology of how you need to approach that. But I think the other aspect, like maybe just a couple of other observations, is it seems to me that collaborations work best when they're joining disparate expertise, where there's not a lot of overlap. So let's say we're a material science group, we're working with a theoretical mechanics group. That's great, because we can't do the theoretical mechanics, they can't do the experimental. There's huge value for both sides. And we're part of different communities. So I'm not giving a talk at the same conference that my collaborator is giving a talk. I usually don't have to worry about overlap. And so you can really parse out the credit, you know, for the work in a really crisp way that eliminates, you know, things that could lead to conflicts, you know, and we can even parse out the papers. You know, we can publish like experimentally oriented paper, and then they can publish a theory paper if they want to do that. Sometimes we join them together, depends on the details. They're going for different awards than I'm going, well, not that I'm going, but my students are going for, whatever. So there's kind of a nice separation that happens if you're collaborating with folks who have expertise that's really different than your own. And I think that applies even to a greater extent when you're thinking about collaboration between engineers and medical folks, you know, clinicians or medically oriented scientists or neuroscientists, for example. There's even a greater separation. So it's even easier, you know, in that sense. And so that's one thing that I would say is important in making a collaboration work well. And then the other thing, you know, for these clinically oriented collaborations, I think our experience is that the doctors are actually great to work with. You know, if you're an engineer, and basically I'm an engineer, you're oriented around solving problems ultimately. I mean, I think most engineers, like you're a biomedical engineer, you want to solve problems, right? And the doctors, the physicians, have a much different language, a much different thought process, but at the end of the day, they're also problem solvers, and they're immersed in a very problem-rich environment. You know, a hospital, they got all kinds of problems, all kinds of deficiencies, you know, in the tools and the techniques and the measurements, and so I think there's a great synergy there. And you know, the question is, how do you bridge the language barrier? And sometimes, you know, physicians don't have a good sense of what are the limits in technology. A lot of them have kind of a sci-fi view of what might be possible, and so you have to kind of, you know, iteratively work back and forth to find things that, you know, will actually work and also address problems. So that's you know, kind of another aspect of things. But I would say it's a great experience for the students. I mean, I think as a faculty member, you're ultimately an educator, and you're trying to create kind of a rich, rewarding, powerful experience for your PhD students and your undergrads as well, if they're engaged in the lab work. And, you know, my experience is that the students get extremely energized and excited about doing research that has some kind of fundamental academic value, but connects to the real world, you know. And when you're connecting to patients and patients' lives and health related issues, my experience is it's even more powerful in terms of a motivating influence for the students. And you get them engaged with the medical community, it really opens their eyes to all kinds of topic areas that maybe they haven't had a lot of exposure to, you know, through their, you know, undergraduate engineering experience. And so I think collaboration is great. It's very powerful. It's a great educational tool, and it ultimately leads to better outcomes. I mean, I think, you know, if you're narrowly focused, you know, on a disciplinary basis, I think you're really constrained in terms of what you can do and what kind of impact you can have. And so I think collaboration is not just a nice to have, it's almost a requirement, you know, for many things, you know, if you want to do things and you want to have an impact. So those are some thoughts. I'd have to think about it a little bit more, but that's kind of top coming real time stream of consciousness type of thing. But the other question had to do like when do you do translation and when do you get things out of the lab? I would say the last possible moment. Keep it in the lab as long as you possibly can, because once you're in a startup environment, you're burning cash like crazy. There's all kinds of overhead. You don't want to put a technology in a startup if you know of any unresolved problems, if there are any engineering uncertainties, if you don't think you know how you're going to manufacture it, if you don't have a pretty good sense of what the cost structure is going to be and what the application requirements will support, don't do it. Because once you start a company, there will be all kinds of problems you don't even know about. And if you know about problems to begin with, you're going to get yourself in a really bad situation. And that, by bad, I mean you're going to be burning cash, and then you got to raise more cash. And as you do that, you lose control of your company because you will be diluted out. The investors will gain a larger and larger percentage of the company, which maybe is not a huge problem, but with that comes control. And once you've lost control, then it's not good. I mean, it's not an enjoyable thing. It's not something that will, have a high probability for success. I mean, things kind of spiral in a direction that probably is not good overall. So my message would be keep it in the lab as long as you possibly can. Get as much testing done as you can. As an academic group, you're much more flexible. You can explore new ideas. You can take risks. You can do all sorts of things. There are all kinds of non-dilutive grants and foundations that you can tap into to support the work. And a startup company is a totally different beast and a different funding model. And you got staff they're drawing down big salaries and all kinds of stuff. So anyway, incubate it as long as you can. That would be my recommendation.
Great, thanks, John. I do have to apologize to some of the delegates, Pinto, Faisal, Benjamin. There are some questions again coming up, and you have partly answered those questions when you talked about nanoribbons, etc. So as I said, I'll pass these questions to you, and in case there are further questions from delegates, you can write to Professor Rogers. So with this, I would like to thank Professor Rogers for this wonderful talk, and I request attendees if you can unmute and clap for Professor Rogers.
Okay, thank you very much.
Yeah.
Yes,
Okay.
yes, it was. Thank you.
Thank you.